A single wind turbine of this type is capable of generating enough energy in one day to supply 100,000 people. We are used to thinking of wind turbines as simply giant fans. But the truth is that inside these giants lies one of the most powerful energy systems ever created. Inside these towers, the flow of wind is transformed into electricity through a highly precise mechanical system capable of withstanding hurricanes and operating non-stop for years. The height reaches 200 meters, and the span of the blades exceeds 150 meters. The power output of a single installation can reach up to 15 megawatts, which is enough to provide electricity to tens of thousands of homes at the same time. Today, we will analyze how a wind turbine is built from the inside. We will show how this machine truly converts wind into electricity and find out whether it can really replace traditional energy sources. Let's climb inside this gigantic machine and see how wind becomes electricity. Imagine you are driving along a highway and out in the fields, huge white towers appear. But they are not towers. They are enormous wind turbines, almost unreal, with blades turning slowly and lazily, without smoke and almost without noise. The first thought is usually, well, okay, they just spin quietly. That is exactly what almost everyone thinks the first time they see a wind turbine, and almost everyone is wrong. The tip of a blade moves at a speed of 250 kilometers per hour as it passes by. That is faster than most high-speed trains. From the ground, you do not notice it because the blade is enormous and the distance is great. The brain simply cannot translate the speed into understandable numbers in time. Try getting closer. At 100 meters from the tower, every pass of the blade feels like a wave of air. The sensation is completely different. A modern offshore turbine, meaning one installed at sea, reaches 200 meters from the base to the highest point of the blade. That is roughly the same as stacking two Moscow city skyscrapers on top of each other. The rotor diameter of the largest models exceeds 150 meters. For comparison, the wingspan of a Boeing 747 is 68 meters. A single blade of a modern turbine is longer than the entire wing of that aircraft. The blade itself does not work like the blade of a fan. A fan simply pushes air. A turbine blade is designed like an airplane wing. One side is curved, the other flatter. When wind flows around this shape, it moves faster over the curved side. The faster airflow creates a low-pressure zone, and this pressure difference pushes the blade forward, exactly like an airplane wing generates lift. It is this lifting force that makes the rotor spin, the entire rotating part of the turbine to which the blades are attached. It is not the direct pressure of the wind, but aerodynamic lift. These are fundamentally different things, and this is precisely why the turbine can operate even in relatively weak winds. The blades are made of fiberglass or carbon fiber. The material is lightweight, strong, and capable of withstanding loads comparable to those experienced by the supporting structures of bridges. Each blade weighs between 20 and 50 tons, depending on its size. Manufacturing a single blade takes several weeks. The mold is filled with layers of fiberglass fabric, impregnated with resin, and baked in an oven. The final product is a monolithic structure with no seams or joints inside. Thanks to this integrity, the blade will not crack under colossal stress. Transporting it to its destination is another story. The tower is assembled from several steel sections, each between 20 and 30 meters long. These sections are transported on special platforms along roads that are inspected in advance for bridges with limited load capacity and curves with insufficient turning radius. Blades, 70 or 80 meters long, are transported at night when traffic is minimal. Offshore wind turbines are assembled using installation vessels equipped with gigantic cranes over 100 meters tall. Installing a turbine at sea takes around 3 days if weather conditions are favorable. At the top of the turbine is the machine room. It is a sealed capsule weighing several hundred tons. It is lifted by crane precisely onto the top of the tower and firmly secured with bolts. A single mistake, while attaching it 150 meters above the water, means the entire installation must begin again. But all this external work is only the first part of the story. The real transformation happens inside. The turbine's machine room is called the nacelle. From the outside, it looks like a white aerodynamic shell about 20 meters long, similar to a large trailer. You can actually enter it. Inside, there is lighting, tools, and enough space for a small team of technicians to work. This is where the main process takes place. The slow rotation of the three blades is converted into electrical current. The main problem is this. The blades rotate very slowly, about 5 to 15 revolutions per minute. That is roughly like the minute hand of a clock, only slightly faster. To generate electricity efficiently, the generator must rotate hundreds of times faster, around 1,000 to 1,500 revolutions per minute. So how do you transfer the rotation of the blades to the generator while multiplying the speed by 100? For this purpose, the nacelle contains a gearbox, a large box filled with gears of different sizes. The principle is simple. A large gear turns a smaller gear, and the smaller gear spins faster. Several sets of these gears connected in sequence accelerate the rotation of the main shaft to the required speed. The gearbox of a large turbine weighs around 80 tons, occupies a significant portion of the nacelle, and costs several million euros. It is also the component that fails most frequently and often requires replacement during the turbine's lifespan. The accelerated rotation is then transferred to the generator. The principle is simple. Magnets rotate inside copper windings, generating electric current in the wires. This principle was discovered by Michael Faraday nearly 200 years ago and remains the basis of all power plants on Earth, from nuclear stations to wind farms. The electricity travels down cables inside the tower to a transformer located at the base, where the voltage is increased to the level required for transmission lines. High voltage is necessary, so energy is not lost in the cables on the way to consumers. Some next-generation turbines eliminate the gearbox entirely. Instead, they use specially designed generators that produce electricity directly at low rotational speeds. This removes the most expensive and least reliable component, but it makes the generator itself much heavier. Engineers still debate which approach is better, and both systems are currently used in real installations. The gearbox and generator also generate a great deal of heat during operation. That is why the nacelle contains a cooling system with radiators and oil circulation, similar to a car engine cooling system, but on a much larger scale. All equipment is designed to withstand temperatures down to -40 degrees Celsius and the humidity of marine air. But even the most reliable mechanism would be useless if it could not adapt to changing wind conditions. That is the job of the next system. Wind is variable. It changes direction, grows stronger or weaker, and sometimes reaches hurricane force. A turbine that simply stayed fixed in one position would be extremely inefficient and dangerous. That is why every modern turbine has its own control system that operates without human intervention. The first task of this system is to rotate the rotor so that it always faces the wind. The tower itself is not rigidly fixed. At its base, there is a yaw mechanism, a system of electric motors and gears that slowly rotates the entire structure around a vertical axis. Sensors on top of the nacelle constantly measure wind direction. As soon as the wind shifts by a few degrees, the system rotates the nacelle to follow it. This movement happens slowly over several minutes, but continuously. Over the course of a year, the nacelle may complete several full rotations around the tower. The second task is controlling the orientation of the blades relative to the wind. Here, it is important to understand one thing. Each blade can rotate along its own axis, like the handle of a screwdriver. If the blade is turned edge-on to the wind, the air simply flows around it and produces almost no lift. If it is turned broadside to the airflow, the lift is maximized, but so is the stress on the entire structure. The angle at which the blade meets the wind is called the angle of attack. In weak winds, the system rotates the blades to maximize the angle of attack, so the turbine captures every gust. In strong winds, the angle is reduced so the rotor does not accelerate beyond safe limits. This process is called blade pitch control, and it happens constantly, several times per minute. When wind speeds reach hurricane levels over 25 meters per second, the system takes drastic action. The blades turn edge on to the airflow, stop generating lift, and the rotor comes to a halt. The turbine enters standby mode. Large turbine towers are designed to withstand side loads equivalent to Category 5 hurricanes. Once the storm passes and wind speeds drop below the threshold, the system restarts the rotor and the turbine resumes operation. All these processes are controlled by an industrial computer inside the nacelle. It collects data from dozens of sensors every second: wind speed and direction, bearing temperature, shaft vibration, blade loads, power output, and more. If any parameter exceeds safe limits, the system automatically reduces the load or shuts down the turbine and sends an alert to the control center. Technicians monitor the status of every turbine in a wind farm remotely from computer screens. Physical visits are only necessary for scheduled maintenance or major repairs. A modern wind farm with 100 turbines can be managed by a team of only a few dozen people. By comparison, a coal-fired power plant of comparable output requires several hundred permanent employees. The turbine's automated system also collects data about every component and predicts maintenance needs in advance. When will a bearing need replacement? When should the gearbox oil be changed? Which blade shows signs of microcracks based on vibration sensor data? This allows maintenance to be planned proactively instead of waiting for failures. But all this precision exists for one purpose: generating as much electricity as possible. And this is where the numbers become truly astonishing. The most powerful production wind turbine today is the Danish Vestas 5236. Its capacity is 15 megawatts. The rotor diameter is 236 meters, meaning the blade span is longer than 2 football fields placed end to end. Under optimal conditions, such a turbine can generate around 80 million kilowatt hours of electricity per year. To understand the scale, an average family of 3 consumes about 3,500 kilowatt hours annually. A single Vestas turbine can cover the needs of approximately 23,000 such families. In terms of population, that is around 70,000 people. Including industrial and commercial consumers connected to the grid, the number rises to roughly 100,000 people under favorable wind conditions. However, one important figure must be understood: the capacity factor. A turbine operates at full power only when wind speeds are ideal. In reality, wind is sometimes weaker, sometimes stronger, and sometimes absent altogether. On average, over an entire year, a turbine produces energy equivalent to about 35 to 45% of what it could generate if it operated at full power 24 hours a day. Offshore installations achieve higher figures, up to 50%, because sea winds are stronger and more stable. For comparison, nuclear power plants operate with capacity factors around 90%, and coal plants around 75 to 85%. This does not mean wind energy is inferior. It means it operates differently, and this difference must be considered when designing an energy system. An offshore wind farm consisting of 100 turbines rated at 15 megawatts each can theoretically generate as much annual energy as an average 700 megawatts coal power plant. But the coal plant generates electricity whenever requested. The wind farm generates electricity only when the wind blows. This fundamental difference defines the entire debate over whether wind can replace traditional energy sources. The expected lifespan of a modern turbine is 25 to 30 years. During this time, scheduled maintenance is required approximately every 6 months. Blades are inspected using drones. They fly around each blade, capturing high-resolution images of the surface. Software then analyzes the images for cracks and material delamination. If a crack is detected early, it can be repaired on-site with special compounds without removing the blade. Missing such a defect could mean losing the entire blade, 20 to 50 tons of expensive material. The cost of a large offshore turbine, including installation, ranges from 5 to 8 million euros, but the fuel for the turbine costs nothing. wind is free. That is precisely why the cost of electricity from offshore wind farms has fallen to less than 1/3 of what it was 10 years ago, and it continues to decline. Denmark, a country of around 6 million people, sometimes generates more than 100% of its electricity demand from wind on particularly windy days. The excess electricity is exported to neighboring countries such as Germany, Norway, and Sweden. On an annual basis, wind power accounts for more than 55% of Denmark's electricity mix, the highest percentage in the world for a large national grid. By the end of 2024, Germany had installed more than 70 gigawatts of total wind capacity. On favorable days, wind supplies more than half of the country's electricity demand. At the same time, the German energy system is designed so that gas-fired power plants can quickly start operating during calm periods, while excess wind energy is exported through the unified European grid. China is building wind turbines faster than any other country. In 2023 alone, China installed more new wind power capacity than the rest of the world combined during the same period. By the end of 2024, total installed global wind capacity exceeded 1,000 gigawatts. But all these numbers share one common challenge: wind is irregular. This creates two major questions for modern power systems. First, what happens when there is no wind for several consecutive days? In Europe, such periods are called dark, windless weeks, cold winter days with weak sunlight and almost no wind, when neither solar panels nor wind turbines generate much electricity. Second, what happens when the wind is too strong and more electricity is produced than the grid currently needs? The answer to both problems is the same: energy storage and flexible grid management. Today, the primary storage method is pumped storage hydropower. This method is heavily used in Norway, which effectively acts as a giant energy buffer for Danish and German wind power. Pumped storage plants use reservoirs at different elevations. When excess electricity is available, water is pumped uphill into the upper reservoir. When electricity is needed, the water flows back downhill through turbines, generating power again. The process is reversible and can be repeated hundreds of thousands of times without significant wear on the main equipment. Norway's mountainous fjords make it ideal for this type of energy storage. When Denmark has excess wind energy, electricity is sent to Norway, where pumps move water uphill. When Denmark lacks wind, Norwegian hydroelectric stations release the water and return electricity to the grid. The entire system operates automatically and responds to changes within seconds. The second solution is hydrogen. Excess electricity is used to split water through electrolysis. The hydrogen is stored and later used in fuel cells or industrial processes. The technology is still expensive, but costs are falling rapidly. The third solution is large-scale lithium battery storage. Such systems are already being built. In Australia, a 300-megawatt battery facility operates as a giant grid stabilizer, connecting to the network within fractions of a second whenever additional power is needed. Wind alone cannot currently guarantee the energy supply of a large country. Not because turbines are weak, they are powerful enough. The real problem is that storage systems and grid management technologies have not yet reached the required scale. That is exactly where the world's biggest energy investments are now being directed. The International Energy Agency predicts that global wind capacity will triple by 2035 compared to current levels. The cost of battery storage has fallen ninefold over the past decade and continues to decline. That gigantic turbine that once looked like nothing more than a beautiful fan on the horizon is becoming one of the planet's main energy sources before our eyes. Subscribe to the channel so you do not miss the next episode. Many more stories await us about how the things we see every day actually work, even though we rarely think about them. See you soon.